So the first one is a pretty simple one, although maybe it's so simple that it becomes hard because it maybe looks too easy or something like that. But in any case, I have it solved here. So to get the derivative at this point, we use f of x minus f of a. F of a, you have to plug in -1 and you get -3. So here's f of x and here's f of a. And divided by x minus -1, so that turns into x plus 1. So the numerator after simplification is this, the denominator is that. We can factor out a factor of 2 from the numerator, cancel a common factor, and the result is 2. Now, if we wanted to find the derivative simpliciter, then we would use f of x minus h. So here's f of x minus h. There is only one variable, and it gets replaced with x minus h. Now, after distribution and canceling certain terms, all of the x's, in fact, vanish, and you're left with 2h over h. The h is canceled. The answer is 2. So one of the things that is kind of a lesson here is well, of course, that the derivative of this at x equals 1 is 2, and also the derivative is just equal to 2. But one thing to think about to kind of confirm, like thinking about the relationship between the derivative and the derivative at a point, is that this is supposed to be a function. Now, it doesn't look like a function, it looks like just a number, but in fact, it is really the constant function, right? Plug in any number you want, and it's just always equal to 2. It's kind of, here's another example of a constant function. G of x is equal to 10. This, you could plug in any value of x you want, the answer is always 10. So this is a constant function. That's a legitimate thing to have, and that's what we have up here. So if you plug in any argument at all, you'll get 2. Well, in relation to the earlier problem, we would plug in -1 and get out 2. It's kind of a trivial instance of the pattern, but it is still an instance. So to illustrate this, or at least confirm it, I'll go ahead and have SimPy run the calculation of the derivative, and it also says 2. So that's right. Oops. Now down here, we find the derivative of 2. So f of x is equal to 2, again, the constant function. F of a, you plug in, f of x minus h, right? That's what goes here since we're finding the derivative simpliciter. So f of x minus h, well, it's the constant function. So again, no matter what you plug in, it's just equal to 2. And we take the difference, which is equal to 0. It does not matter what the value of h is. This just simplifies to 0. And again, we can not only compute the derivative, but this time, just to make sure it's clear, I'll also plot the function, right? I'll plot the function which is just equal to 2. Now, ignore this noise over here because SimPy just won't let me plot the number 2, right? It regards it as a number, not as a function. And so it gives me little complaints and mistakes over here. So I just throw in something that I try to make as small as I can, just so that it thinks of it as a function. And that's the only reason that's there. Really, this should just be 0, and there shouldn't be anything. But if I put nothing there, SimPy would not know what to do. So here I plot it. And this is the graph of the function. Now, for whatever reason, it cut off the y-axis, but it's not really necessary. You can see that it is the constant function 2. Yeah, that is f of x, right? This is the function. F of x is equal to 2. So if you plug in any x value at all, the output, the y-coordinate, is always equal to 2. So that's what a constant function looks like. Okay, moving on to the next problem. We want to find the derivative of this at 1, and that means finding f of x, which is x cubed minus 1, then f of a, which you plug in 1 and it evaluates to 0, divided by x minus 1. Now the numerator factors into x minus 1 blah blah blah, right? Factorization of perfect cubes. And the x minus 1 factor vanishes upon cancellation. And at that point, we can just plug in the limiting value, or well, the point to which we are approaching, if I want to use the right terminology. But basically, that just means plugging in 1. And when you do, it calculates to 3. So we want to also find the equation of the tangent line. We need to know a point on the line, but we get that by plugging in 3 back into the original function to get a point on the graph, and that is 3, 0. Now we use the point slope formula to get the formula of the line, and I'll just leave it at that. Although down here, I actually plot the two functions. And there it is, right? So this is x, the blue line is x cubed minus 1, and the red line is the tangent line, which we found by doing this here. And then I just kind of input it through SymPy as this, right? So just solving for y. Anyway, is there anything else to this problem? Right, so also find the derivative of x cubed minus 1. So here I have x cubed minus 1 minus, now this is f of x minus h. There's only one place to plug in x minus h, that's into the x cubed part of it. Now I have to multiply out a cube. I went ahead and did the gory details right here. You could use the binomial theorem if you're familiar with it to get that result, or you could just multiply out 3 things and spend a bunch of time regrouping and simplifying, and after all that work, you will have this result. So then, after distributing the negative and canceling with some of the terms that are over on the left, you result in this. And at that point, you can divide by h, cancel factors of h. Wherever factors of h are left over, recall that we are taking the limit as h goes to 0. So wherever factors of h are left over, they just vanish. And the only thing that doesn't vanish is where a single factor of h cancels. And that leaves us with 3x squared. So on to the next problem. We want to find the derivative of the square root and use it to find the tangent line at x equals 4. Well, I'm going to start with just the derivative, actually it looks like I calculated the derivative at the point x equals 4, so I'll just run with that. We would have x square root x minus, f of 4 is equal to 2 in this example, and divide by x minus 2. Multiply top and bottom by the conjugate. I promise this is the result of multiplying top and bottom by the conjugate. A common factor cancels. You plug in 4, and you get 1 over 2 plus 2 is 1 over 4. So to get the tangent line, we plug into the point, right? We plug in 4, get out 2, so that tells us the point on the line, and then we use point slope to get the equation of the line. Next, we find the derivative of this and use it to determine where the function is increasing and decreasing. So here is the calculation of the derivative. Notice that where you have x squared, in this part of the definition of the derivative, we replace it with x minus h. And in this part, where you had minus 5x, you replace it with minus 5x minus h, like that. After distributing, multiplying, regrouping, canceling, so on, you get, hopefully, this. You then cancel any factors of h wherever you can, and whatever has an h left over goes to 0. So this is the limit. We would like to use this to decide where the function, this function, is increasing or decreasing. And so to find out where it's increasing is to find where the derivative is equal to, is positive. So we set it to be positive, solve for x, and we get that it is increasing where x is greater than 5 over 2. And notice 5 over 2 is 2.5. That's right here. It is increasing where x is bigger than that. So in fact, you can see it in the graph if you care to graph it. And if we set this less than